And we're back. Let's continue on talking about types of work. So we've talked a good amount about heat transfer. Let's talk about types of work now. So different types of work you can see here. We're going to walk through and talk about a few of these. So if we do that, right, you've got your traditional applying force through a distance. That is very simply where you've got work is equal to the integral of that force with respect to distance. Very similar to what hopefully you saw in a Physics 1 class. But it's very rare in this class that we'll have to actually just take a force and integrate a force through a distance. But it's not out of the realm of possibilities. Hmm. More likely, the situation is we've got some other type of force causing that distance travel, causing the work to be done or transmitted. And they often take the top two there is expanding gas and then also the idea of electrical work. These are the two most common ones that we'll encounter. We'll encounter rotating shaft work quite a bit. Occasionally, we'll encounter a spring. And you can also find these in the problem sets. But so expanding gas, we look at that for gas expanding in a cylinder. And we're going to look at this very heavily in chapter 4. It's kind of the whole foundation of chapter 4. If I noticed in recent editions of your text, they basically have phased this discussion out of the chapter 2 discussion, but it's okay to explain it just a little bit. If I've got an expanding gas, like it's some gas trapped in a cylinder or some other closed system where that system can expand or contract, then we can calculate the boundary, what we call the boundary work, the work done by the boundary to either expand or be compressed. And if we compute it in the out direction, that means we will be computing the result of pressure causing the force. Now, of course, pressure is force per unit area. So force would be pressure times area. And if I take area times distance, I get volume. So pressure with respect to volume, the pressure is what actually generates the force inside a system or external of the system. And the change in the volume then represents the change in distance for our system. So this is, again, I'm introducing it here, but this is a concept that we're going to see chapter 4 and beyond. For us, it's going to be exam 2 material and beyond. Very common thing that we're going to encounter. It's okay to mention it here, and we really don't need to dwell on it any more than that. But something that you will see throughout the semester, starting here in chapter 2 and working our way throughout, is electrical work. Now, if we start with power, electrical power, that would be W dot. Power is a rate of work energy, and we'll subscript it with an E because it's electrical. That's going to be a quantity that we call voltage. Yet another V quantity. This is voltage times current. So voltage, if we oversimplify this, right? Voltage would be basically how hard the electrons are being pushed to flow through a circuit or through a system. Um, it's a bit of an oversimplification, but that's a reasonable description. Voltage is how hard we're pushing the electrons to flow. Current is measuring the rate at which the electrons flow, basically. It's the flow of electrons. And that's what generates electricity, and that's how electricity transmits energy is by the motion, the coordinated motion of electrons. What causes the work to be done is it's essentially a magnetic force or a magnetic field being generated by the flow of electrons or a magnetic field causing the electrons to flow, is kind of the way I think of that. And that's the force then that's being applied to transmit this work that's being done. Now, this represents the voltage times the current which again, this is often another V times your text uses a capital I. I know some electrical science texts will use a lowercase I for current. Sometimes I've seen J used for current. Your text here, the thermotext, is going to use a capital I to represent current. Yes, that's another V. It's going to look just like speed. That's honestly, we don't use electrical power very often or deal with electrical energy very often. So a lot of times I just simply write out the word voltage because it's so rare that we use it, but we do encounter it from time to time. Now, again, this is power. Notice the dot here. This is the rate at which electrical work is being done. If I need to find the amount of electrical work that has been transmitted, the amount of electrical work being done, I need to integrate this electrical power with respect to time from basically over my change in time from the initial to the final time. Now, if voltage and current are constant, we call this direct current or DC conditions. So if voltage and current are constant, then that means that their product, right? So if notice these guys out here, if these are constant, their product is constant. So their product is not changing with respect to time. So I'm just integrating a constant with respect to time. That's, as I've said earlier, that is the easiest integral. If we have what we can treat, if we have what appears to be or something we can treat as DC conditions, basically the power tells me the rate at which work is being done. And I just need to multiply that by the amount of time over which that power is being transmitted. And that will give me the amount of work being done. Okay. So not too complicated. That's a pretty common thing that we'll encounter. I might need to find the voltage or the current, right? Units here, if I to the side over here, for our purposes, we can just treat 1 volt times 1 amp. We can just treat that to be 1 watt, which is, of course, 1 joule per second. 1 volt times 1 amp is 1 joule per second or 1 watt. There's not really any English units for electricity. Our understanding of electricity evolved after the SI system was developed, so there really isn't a need for English units. I mean, you have kilowatt hour, that's about as close as it is, but that's based off of watts. So anyway, rotating shaft work. Just a second. So rotating shaft work is something that we will often, it's very rare that we're actually going to have to calculate rotating shaft work. But if you do, just understand if I've got a shaft rotating, basically the force that's being applied is equal to a quantity we call the torque divided by the radius. And this would be the radius of the shaft. And the distance traveled would be how far we travel per rotation. So that would be 2 pi r would be the distance traveled per rotation multiplied by the number of rotations. So again, T, this capital tau here is torque. R is the radius of the shaft. N would be the number of rotations. And so if both torque and, I'm sorry, well, yeah, if both the radius is going to be constant. So as long as the torque is constant and, yeah, if we're applying constant torque, Well, then the work just ends up being there's no integral needed because everything's constant, force times distance. Well, torque divided by R times 2 pi R N just simplifies to be 2 pi times torque times the number N. Mhm. And if it's rotating at a specific rate, or you want to know the rate at which work is being done, well, that's pretty simple. That's 2 pi times the torque times the rate of rotation in dot. That's RPMs of, like rotations per minute is a way of measuring in dot, basically. All right. So again, we don't have to dwell on that too long. I did want to show that to you because you will encounter some problems in the text that from time to time, or maybe online, where yeah, maybe they give you torque and they give you the rotation rate. It's a very simple calculation to figure out the work being done. We just need the amount of time and the rotation rate and the torque. We're good to go. Occasionally, you will encounter a spring. So if I have a spring, that's a variable force. Force is based off of the stiffness of the spring or the Hooke's law constant times basically the S value, how far you've compressed or stretched the spring. So what happens then is the work, because we're going to integrate that force with respect to S, well, this just becomes um, that's regular equal sign. This becomes K over 2, the stiffness or the Hooke's law constant of the spring, times the change in the length of the spring squared. And the difference of the lengths of the spring squared, I should say it that way. Um, yeah, so this would give you the amount of energy stored in a spring, whether it's being compressed or stretched, based on how far it goes from the initial position to a final position. Okay. So again, you won't encounter shaft work or spring work very often, but if you do, here's basics. They're actually pretty simple to compute and determine and calculate. But again, you will encounter electrical power from time to time, electrical work from time to time. And when you do, when you find that, what I don't want is you to have no idea what to do with it because we've talked about it. It's covered in chapter 2 in your textbook. You're responsible for the stuff that's covered in your textbook. So you can either go back to chapter 2, or you can go back to your notes over this section and it's covered here. Okay. And then again, we will talk more about expanding gas boundary work throughout the semester. So you can look at it here, but we're going to talk more about this later. Okay. All right. And if you do encounter a problem in the homework, if you're working extra problems, which is always a good idea, I'm probably not going to assign you something where you need to calculate shaft work directly or find the energy stored in a spring. But if you do, here it is. Last thing I can mention here, yeah, I've got a minute or two here, and then we can look at some example problems. This idea of efficiency, right? So efficiency is going to be a quantity that's less than or greater than um, zero. It's basically from 0 to 100%. Efficiency is unitless. So this is how I would draw that eta. That's a Greek letter eta. Efficiency is unitless. It's a ratio. Your textbook loves to call it output over input, and that works a lot of the time. So this idea of output over input, that's okay. I would always suggest the expected expected I think I spelled expected wrong. The expected smaller value divided by the expected, let's see if I can spell it right this time. Expected, I think that's right. Larger value. And I paused for a minute or two. I'm not quite at 15 right now. What do I mean by that? Expected smaller value divided by the expected larger value. Well, what we're trying to say here is if it's a true efficiency, nothing's ever 100% efficient, right? Well, nothing's ever more than 100% efficient. The second law is going to show us later that nothing's really ever going to be 100% efficient. If it's a true efficiency, it's going to be between 0 and 100%. So what I'm saying is the quantity that you're going to put on top of the ratio for an efficiency should always be whatever you expect to be smaller. So for example, if you look at your cell phone charger, this is something I'll point to a lot because it's something that you probably have laying around. Or, I don't know, you probably maybe just, I don't know what you plug your cell phone into to charge it, but you probably charge a cell phone. Some device is converting electricity coming from your wall, that's AC 120 volts all the way down to 5 volts DC, and you can feel it's putting off some heat. It's not 100% efficient. So all of the electricity that's coming into that thing is more than the electricity that's actually going into your cell phone. So you would expect the energy going to your cell phone to be less than or smaller than the energy that your phone charger is actually consuming. So you would put the electricity going to your phone charger in the numerator because we expect that's the smaller quantity divided by the electricity going into your charger, your input in this case, you're going to put that in your denominator. But you're going to have to make sure the units are the same. So that means if the units are the same, that means your dimensions have to be the same. I have to put power over power, or I have to put energy over energy, or whatever it is that I'm trying to compare. I have to have the same units because again, efficiency is a unitless quantity. And if it's unitless and I'm comparing correctly values, I will get a value between 0 and 100% time. And just kind of point out a few things here. Efficiencies stack, right? So efficiencies will stack together. So what that means is if I have a system of multiple components, each component has its own efficiency, and you multiply those efficiencies together to determine the overall efficiency of the whole system. So if I've got a gas power generator, for example, where I've got an engine, I've got some kind of an engine over here that I pour gasoline into, and that's going to have a certain amount of efficiency that it's going to generate. So maybe, I don't know, 40% efficient. And then we've got an electrical generator turning some magnets around, pushing wires through, or pushing electrons through coils that pushes then electrons through my wires. This generator portion is only going to have a certain amount of efficiency. I don't know, maybe 60% ballpark. So overall, you might have a 24% efficiency because you're going to have whatever this efficiency of the engine is multiplied by the efficiency of the generator and the product of those two, which is they're both going to be less than 100%. So your overall output is going to be even less. So every time you stack components together, you end up with less and less efficiency. Now, you can have devices that are highly efficient, like gears in a drivetrain, for example. They tend to be about 90 to 95% efficient. But if I've got 5 gears stacked together, I'm multiplying 0.95 by 0.95 by 0.95. After enough gears, you do start to lose some efficiency. And that's with highly efficient components. Okay. So we've introduced the concept of efficiency. We don't have to dwell too long on that because we're going to work a couple of examples coming up.